Hello and welcome everyone. In this video, we will look at a modified Euler's method which is known as Heun's method. In the previous videos, we have seen that higher order Taylor series methods are more accurate than Euler's method. However, these methods also require calculating complex higher order derivatives which can be challenging. Let's see how Heun's method improves the accuracy of Euler's method and still avoids the complexity of higher order Taylor series methods. Let's say we have a function and we are given the value of y at an initial x position. These are our initial conditions. And from our ODE, we can get the slope at this point. In the Euler's method, we use this slope or tangent line to predict values at the next step. We'll call this a predictor equation. In the modified method, we further compute the slope using the values from the predictor equation at xi plus 1. Now we use both slopes, one at xi and one at xi plus 1, to compute the average slope for the interval. And finally, we use this average slope to extrapolate linearly from yi to yi plus 1. This final equation is called a corrector equation. Let's now see how we can use Heun's method to solve the first order ODE that we solved in the previous videos. We can see Heun's method is more accurate than Euler's method. This is due to its second order error term, so error reduces faster than Euler's method as step size decreases. The step size in this case is 0.2. Heun's method also avoids the complexity of higher order Taylor series methods by not requiring higher order derivatives. This is the code used to find the solution of the above ODE in the given interval. As you can see, this is similar to Euler's method. We only changed the code in the while block. Thanks for sticking around. If you enjoyed this, give it a thumbs up and subscribe for future content.